All right, so we spent last week talking about substitution reactions and elimination reactions, both of which are reactions of alkyl halides. Today we're going to talk about the competition between the two of these reactions. So competing substitution and elimination reactions. Okay, so first of all, let's talk about why there is a competition between these two. We talked about how substitution reactions they required what are called nucleophiles. And nucleophiles are these electron-rich molecules. And then when we were talking about elimination reactions, one of the key steps in these elimination reactions is removing a hydrogen from a neighboring carbon. So these require bases or hydrogen acceptors. All right, so we have one category of reaction that will use nucleophiles. The other category of reaction uses these bases to accept hydrogens. All right, but again, these two are in competition, so why is that? All right, that is because many molecules are both bases and nucleophiles. Right, so one category of reaction requires nucleophiles, the other one requires bases, but some molecules are both. All right, so a good example is the hydroxide ion. We can see just from our structure here that that oxygen is indeed very electron rich. It's got those 3 lone pairs and that net negative charge. So it is a nucleophile. All right, but one of the very first things you would have learned about hydroxide, one of your very first introductions to hydroxide would have been that it is a strong base. Right? It is also an H plus acceptor. Which again we call a base. Right? So this is a good example of a molecule that is not one or the other, but is both at the same time. It is both an electron-rich species, so it can undergo these substitution reactions, but it's also a good proton acceptor, so it can play the role of a base. Right? So if we mix this in with an alkyl halide, we're going to have a competition between these two reactions that occur. A competition where some molecules will react with this substitution type reaction, and other molecules are going to react with this elimination type reaction. Right? So we got a competition between the two here. Okay? Cool. All right, so I'm going to introduce you to this little chart that you're going to have as like your constants page for this exam. You can find it under the Chapter 6 introduction module as well. All right, rather under the Chapter 6 module on the introduction page here. Or rather on the introduction, holy crap. Let me start over. You can find it under the Chapter 6 module on that very first page titled Chapter 6 Introduction. There we go. Okay. So here is our table here. Again, this is posted on Canvas. If you want to take a picture of something real quick, that's cool. Really importantly, what I want you to have in your notes for sure, because we're going to build off of it, are these headers here. right? So what we can see is we have these 4 categories that we've divided these molecules into. We have our molecules that are strong bases but weak nucleophiles. We have our molecules that are good at both. They're both strong bases and strong nucleophiles. We have some that are crappy bases but really good nucleophiles. And then we have others that are just kind of bad at both. All right, our weak nucleophiles and our weak bases. So these are these 4 important categories here. All right, so I'll give you a second to kind of make your little chart here. And importantly, you want to leave a good amount of room, because what we're going to do is we're going to kind of build with some notes off of this down at the bottom here. All right, so first let's take a look at these, different molecules that are contained in here. You see that we're written in our condensed structural formula, so here's a good indication of where we're going to use those, right? Because we want to fit in this nice little compact space on our table here, okay? We see a lot of R's going on here, right? RO, R2, R. What does the R stand for again? That's an alkyl group, so any number of carbons and hydrogens, or just hydrogen. All right, so it's a compact way of saying it doesn't matter how big it is as long as it has that sort of functional group on there. So for example, RO minus. All right, this can be any one of these molecules, any number of carbons. So this would be an RO minus. Notice how they're lazy and they don't put in our lone pairs here. Can't really type in lone pairs on our computer. But it doesn't matter whether it's 1 carbon, whether it's 1,000 carbons, or whether it's just a hydrogen, right? All of these fall into that same category of ROH. R is kind of like a variable, meaning any number of carbons and hydrogens, any size alkyl group. Okay, so before we move on here, let's take a look at this one, RSH. Give me an example of a molecule that fits that formula there, RSH. So that could just be 2 H's and an S, or I guess we could write it HSH. Could have 2 carbons and an SH. Could have 1,000,000 carbons and an SH. All right, all of those would fall under that category, RSH. A few more of these I want to point out explicitly. So first of all, Cn-1. We've taken a look at this Lewis structure before, but it's really deceptive how it's written here. All right? If we draw out our Lewis structure, we have a lone pair on the nitrogen and a lone pair on the carbon. But which one of those actually has that net negative charge? No. My nitrogen likes to have how many bonds and how many lone pairs? 3 bonds and 1 lone pair. My nitrogen's perfectly happy here. It's the carbon that's got that net negative charge. This is what we put under that carbon nucleophile category. So again, it's a little misleading with the way that it's written here. We just know, because there's no way to draw this molecule with the nitrogen with a negative charge, that this is the same thing as this structure here, but maybe we want to have that in our notes to be clear. Another one is RCOO minus 1. So now we have that R group, any number of carbons attached to this carbon here, right? But this carbon's got now 2 oxygens on it. One of them has to be double bonded, and the other one single bonded with that negative charge. All right, when we were talking about our condensed structural formulas, we said COOH. That's how you know you have a carboxylic acid group. So without the H, you have that deprotonated carboxylic acid group. All right, and then we only have one molecule here under our strong base, weak nucleophile category. Everybody take a second and draw out the bond line structure for that strong base, weak nucleophile. All right, so given our condensed structural formula, CH3, there's 3 of them on a carbon attached to an oxygen with a negative charge. That would be this structure right here, kind of a plus sign with a negatively charged oxygen on there. Okay. I'm going to keep it like this on our constants page on our exam. I'll just sort of note here, the name of this molecule is tert butoxide. And so some textbooks will write this as TBUO-. I don't find that to be particularly helpful. Doesn't really tell you what the structure is, but you will see that many places for that particular molecule. All right, so we have a bunch of different nucleophiles and bases arranged into these 4 categories here. Again, we have things that are good bases but bad nucleophiles, things that are bad bases and good nucleophiles, things that are good at both, and things that are bad at both. Right? Those are our 4 categories. All right, so again, this is what's going to be given to you on your exam, on your constants page. All right, what I'm going to expect you to be able to do is to make this little chart here. What we're going to do is for each category, we're going to create 3 rows. All right, and each of these rows represents our different classification for our alkyl halides. So we're going to have one row for our primary alkyl halides, another for our secondary alkyl halides, and then a last category for our tertiary alkyl halides. All right, and for each one, we're going to say, all right, if we combine these with one of our nucleophiles, what's going to be our major product? A substitution product or an elimination product? All right, so we're going to make this little chart here. We're going to see that whether or not, these two reactions are in competition, substitution and elimination. Whether or not one predominates over the other is going to depend both on the type of nucleophile/base we use, but also the type of alkyl halide that we start with. So I guess let me be clear. These are our alkyl halides. Okay? So, again, on your exam, I'm going to give you this top part here. I'm going to expect you to be able to fill in this table on your own. All right, so 2 of these columns are kind of the most straightforward. All right, so let's think about it. If something is good at being a base, but a terrible nucleophile, what type of reaction would we expect to see? Substitution or elimination? Elimination. Remember, elimination requires bases, substitution requires nucleophiles. So if something's a good base but a terrible nucleophile, that's going to undergo elimination reactions. All right, so our first category here of strong bases and weak nucleophiles, these are going to prefer elimination reactions. All right, and we only got that one molecule in that category, so let's just take a second to talk about why this is. This molecule has that oxygen with a negative charge. It's got that very electronegative oxygen that's got a lot of electron density. So why is this thing so bad at being a nucleophile? Well, because it's got this big bulky back end to it here. This is a category of bases we would call a bulky base. Which means that it just simply cannot access any sort of a carbon to undergo a nucleophilic substitution reaction. Right? It's just too big. So these will prefer those elimination reactions. And then let's go to the other extreme here, our weak bases and our strong nucleophiles. If something is a crappy base but a good nucleophile, what do we think that's going to prefer? Substitution. So again, good nucleophile, crappy base, we're going to see substitution reactions. right? One thing that we're going to kind of add here just to make our lives a little bit easier, just to remind ourselves here, when we talked about these substitution reactions, we had this stereochemistry part of it. Do we flip our dashes and wedges or not, right? So which one of these three categories, primary, secondary, or tertiary, did we see that stereochemistry inversion for? The secondary. So let's just make a note. We have that stereochem inversion to worry about. For primary, we said we didn't have to worry about it at all. For tertiary, we don't really have to worry about it other than the fact that we lose that stereochem, right? So any dashes and wedges about that electrophilic carbon just become those straight line bonds. All right. So these two categories, these two columns are kind of the easiest here, right? Because we have things that are good bases but bad nucleophiles. Well, bases prefer elimination reactions. And if you're a bad base but a good nucleophile, then you're going to prefer substitution reactions. So now let's go to the mix of both here. What about something that's a weak base and a weak nucleophile? All right. We had talked about weak nucleophiles in particular before, and there was only one type of alkyl halide that can react with these weak nucleophiles, and that was the tertiary alkyl halides. So we're not going to see any reaction between primary and secondary in this category. Okay? But for our tertiary alkyl halides, because these aren't really great at being both, these reactions will occur with about a 50-50 split. We're going to see about half of our molecules undergoing elimination, and the other half of our molecules undergoing substitution. If we want to just note, because we're tertiary, we got to lose that stereochem. Okay, so this last category, the strong category, is kind of the trickiest, or rather I think just takes a little bit more logic to explore here. So let's just take an example of our strong base, strong nucleophile. We'll use our hydroxide ion. We like that example. And we're going to look at it with a primary alkyl halide. Secondary alkyl halide, and a tertiary alkyl halide. Right, so again, this is our example for a primary, secondary, and tertiary. And for each of these, we're going to react it with that hydroxide. Now, let's just imagine that we're looking at substitution reactions here. In order for that substitution reaction to occur, that nucleophile has to be able to attack that electrophilic site, that electrophilic carbon. And what we want to do is we want to look here and ask which nucleophile is going to have the easiest time attacking. Right? That nucleophile has to go and form a new bond with that electrophilic site. So it's got to get in there and react with that carbon. Well, which one of these and which one of these examples is that nucleophile going to have the easiest time reaching that carbon? Primary, secondary, or tertiary? Primary. Why primary? Because there's nothing in the way, right? It's not all crowded up. All right, so we talked about this last time. Molecules, they don't like being next to each other, what we call steric hindrance. So the bottom line is here, in our primary alkyl halide, our carbon is very accessible, aka very easy to get to. There's not a bunch of other big crap in the way that's blocking it up. If we have a secondary carbon, if we put it into the middle of the molecule, now it's kind of accessible. But it is kind of sandwiched between these two carbons, so it's in a much more crowded environment. Our nucleophile is going to have a much more difficult time getting in the way, or getting to that electrophilic site. And then if we have a tertiary carbon, this is not at all accessible. All right, you're going to have a much more difficult time getting that nucleophile to that very crowded tertiary site. So in terms of these substitution reactions, which one is going to have the easiest time attacking? Well, primary is going to be better than our secondary carbon, which is better than our tertiary carbon. And if it can't get to that carbon to undergo a substitution reaction, well, then it's going to instead do an elimination reaction. So in terms of our ranking for substitution, but if we were to flip things around and do the reverse elimination, that means that the tertiary is going to be more likely to undergo elimination than the secondary, which is more likely than the primary. So if we go back to our little chart here, that's going to be reflected in these three boxes. Our primary alkyl halides are going to greatly prefer substitution reactions. The major product of those reactions will be substitution. You might get a little bit of that elimination product, 10, 20%, something like that. But because that carbon is super accessible, that nucleophilic character of that molecule is going to take over. And when we get to a secondary carbon, now we're going to see these are flipped. We have much more elimination product and only a minor amount of substitution product. This is still a secondary alkyl halide. So if we're going to have our substitution product, we're still going to remind ourselves about that stereochemical inversion.
What would you say the percentages would be the same? 20?
It really is, the devil's in the details there. We're going to go for major and minor, not kind of throw numbers at it. And that's just going by this trend here, what would we expect for tertiary? What would we expect our major product to be? Elimination or substitution? Elimination. And in fact, that carbon is so incredibly crowded that you will get virtually no substitution product at all. The vast majority, 99.9% now we're talking, is going to be that elimination product. All right, so why is that again? How did we explain these rankings here? Again, it has everything to do with accessibility. All right, if I'm going to keep one key word in my mind to help me figure out how to fill in this category right here, it's how accessible is that carbon to a nucleophile. Okay, cool. So what we have here is kind of like a little bit of a cheat sheet that we created, where if we're given an alkyl halide, we figure out what category that alkyl halide is. We're reacting it with something. We're going to figure out what category that is. And that tells us whether we're going to have our major product as our substitution or our elimination product. All right? Again, on an exam, you're going to be given your nucleophile base cheat sheet here. And one of the very first things I'm going to tell you to do is to fill in this chart right here. This is what I expect you to be able to fill in, right? And then you're going to use this going forward throughout the rest of the exam. Okay? So let's put this into practice right now. So we'll take this same alkyl halide here, and we're going to treat it with two different reagents. So what I'm going to do is I got to figure out what category my alkyl halide falls into. What are we looking at here? What is this alkyl halide? Primary, secondary, tertiary? Primary. Right? The carbon with that halogen on there only has one carbon neighbor. And then I got to look at my reagent here, and I got to figure out what category that belongs to. SH with a -1 charge. Who spies it? What box are we looking at here? Weak base, strong nucleophile. This thing right here. So for a primary alkyl halide and a weak base, strong nucleophile, we should be seeing a substitution reaction. So I'm going to substitute that alkyl halide for that SH. Boom. All right, again, because we have we're going to say this is a strong nuke, weak base category. That gives us our major product as a substitution product. So then for my next one, I'm going to play the same game. All right, we got a same one, so obviously same primary alkyl halide. And then what base, what category does this molecule fall into? This is our tert butoxide, that strong base, weak nucleophile. So this one's a good base, but a crappy nucleophile. And they will undergo, again, I guess we can just look at our chart here, right? Primary with a strong base, weak nucleophile. That means we should see that elimination product. Okay. As we discussed last class, the elimination products are pretty difficult to get to. Hopefully everybody practiced that over the weekend. In this case, there's just the one because it's a fairly simple molecule. We have just our one propene here. Okay? But again, that's the name of the game, right? We all see what we're doing here. We're going to look at what category our alkyl halide falls into, what category our reagent falls into, and then we're going to check our little cheat sheet here to see what our major product is for our reaction. Okay? All right, let's do another one. All right, so last time I picked the same alkyl halide and chose different reagents. Okay, this time we're going to keep the reagent the same. We're going to use one of those deprotonated alcohols. I'm going to switch up my alkyl halide here. I guess to be clear here, I'll ask just for the major products. All right, for this first one, what's our category for our alkyl halide? No, I'm sorry, for the alkyl halide. Classification, primary, secondary, tertiary. Primary. And then what about our reagent here? So that one's the strong nucleophile slash strong base. This one's good at both. All right. So if we look at our category here for a primary and a, specifically this one here, our strong base, strong nucleophile, our major product will be that substitution product. All right, remember when we draw our major product, when we draw our substitution product, we're going to need to connect that electrophilic carbon to that nucleophilic oxygen. Oh, 1, 2, 3, 4. All right, always a good idea to count carbons. I almost messed that up. 1, 2, 3, 4. And then I got these extra 1, 2 from my nucleophile here. All right, so we look it up on our little cheat sheet. We see that our major product is that substitution product. All right, we're going to keep this nucleophile the same, our our reagent the same, strong nucleophile, strong base. But now what's the classification of our alkyl halide? Now we have a tertiary alkyl halide. And because those tertiary alkyl halides are so crowded, we're going to, instead of having a substitution product, we're going to get that elimination product. All right? Now this one was a little deceptively tricky because our elimination products should be those alkenes, but there are two different alkenes that we can get from this molecule, starting from this alkyl halide here. All right? We're going to form a double bond between that carbon that's attached to that alkyl halide, but also one of its neighbors. And I have two distinct neighbors here. To be clear, if I picked either one of these two, I would get the same molecule. So here's one possible elimination product. Or my double, so if it forms between one of those orange carbons. Or it can form in the other direction. That green carbon. I specifically asked for the major product here. So which one's going to be our major product? The one on the left or the one on the right? The one on the right. So this would be our answer here if I asked for the major product of this reaction. All right, so again, we're going to get our category of our our category of our alkyl halide and of our reagent. We're going to look it up on our little chart, and that's going to tell us whether we're going to be doing a substitution or, in this case, an elimination reaction. Okay, so now let's do kind of worst case scenario. I want you to draw all possible products and label the major product. No. What's up?
I wrote my chart wrong.
Okay. All right, I will put this back up here. So you make sure to find our category. so let's look at our, first of all, alkyl halide, what? Primary, secondary, tertiary. So in this case, we have these secondary alkyl halides here. So let's make sure that we can take this nucleophile, figure out what category it belongs to here. All right. Let me do this. Cool. All right. So this thing here, what category would that belong to? Weak base, strong nucleophile. So that's this thing right here, right? An R group is any number of carbons. In this case, it's just one plus that SH. So for our secondary alkyl halide, we're only going to see that substitution product, all right? We do have to remember our stereochemical inversion. The other thing we have to remember is sulfur is kind of weird. Most of our strong nucleophiles have a net negative charge. Sulfur is one element that's really good at being a nucleophile and a really crappy base. So it works even when it's neutral. And we have this neutral nucleophile. So when we attach it, what are we going to have to remember to do? All right, let's see here. I'm going to do my stereochemical inversion. That dash is going to become a wedge. When I put that neutral nucleophile on there, what's wrong with this? It's too much, too many electrons here, right? We got to remove a hydrogen for our neutral nucleophiles. So even though I start out with SH, when it gets attached, it's only going to attach as that sulfur. All right, all of our neutral nucleophiles. So note, that's the case for that sulfur, for that thiol, as well as all of our weak nucleophiles over here. These are all neutral as well, which means that if we're going to attach them in a substitution reaction, we need to remove a hydrogen. All right, and in this case, that was the only product that I got. So boom, major product, done and done. Okay, but again, just wanted to do this example so that we can remind ourselves that our neutral nucleophiles, we need to make sure to remove a hydrogen when they are being nucleophiles, when we attach them to our molecule. All right, and then this one here is going to be especially big pain in the butt here, because what is our category of, let's just take this and look at our chart, make sure we can spy this on here. All right, which one of these do we got here for our what's called an amide ion, NH2 with a negative charge? What category does that belong in? Strong nucleophile, strong base. That is this thing right here. Remember, R's can be alkyl groups or just hydrogens, as is the case here. And importantly, that nitrogen has that negative charge. And since we have a secondary alkyl halide and a strong base, strong nucleophile, our major product's going to be the elimination product, but since it asks for all products, I'm also going to have to include that minor substitution product. So let's do that one first. That one's kind of the easier of the two, I think, because I'm going to remember to convert my wedge to a dash. Since it's a negative nucleophile, I don't have to worry about taking away any hydrogens or anything like that. It's going to go boom, boom. One lone pair. But that is, again, one of our minor products, that substitution product. All right, and I'm going to tell you that there are 3 possible elimination products. I want everybody to take a minute, if you have not already, tell me what those 3 possible elimination products are. All right, so remember when we do our elimination products, we're going to get rid of that halogen, but we also need to get rid of a hydrogen on one of our neighboring carbons. So if we get rid of a hydrogen on that red carbon, that means that we'll have that terminal alkene, our double bond on the very end. Or we can get rid of a hydrogen on the other side. Boom. But then I told you that there was a third product. What's our third elimination product here? Yeah, absolutely, right? So if we look at that blue carbon there, all right, this is that alkene in the trans conformation. And if we swap, if we look here, and we can pick either side, it doesn't matter. Oops, I'm going to draw in my implied hydrogen. Well, I would get a different product if I swapped these two groups here. That would be my cis alkene. I'm going to draw my double bond, but now I'm going to draw that hydrogen over here and that methyl group pointing up. And that would be my other stereoisomer, my cis alkene. All right, so here are all 4 of my possible products. If I mixed my alkyl halide in with this amide ion, we would get a mixture of all 4 of these products. But which one is going to be in the highest percentage? Which is going to be my major product? Transalkene, that one in the very middle here, because it is the most substituted and it has those 2 big bulky carbons on opposite sides. All right, so again, kind of worst case scenario here, because we got a bunch of minor products to draw in as well, and then we've identified what the major product is for our reaction. Cool. All right, I kind of made an executive decision on this particular unit, which is we're supposed to have like an alcohols lecture, and I think it'd be better served if we just kind of set aside a lecture to practice this sort of stuff. All right, so we're going to kick alcohols to the next unit, and we're just going to continue to kind of practice this stuff next class period, all right? I'm going to put together like kind of a little bit of a few practice problems or something, and that's just what we're going to work through next class period, okay? So we'll wrap it up here. I want you guys also, if you had not, there's a few people that have not even attempted those assignments, and I know that they're difficult. You're going to be screwed, all right? Just go in and try it. At least get all the questions that you need, like all the confusion that you have, come in here with that, and let's get it all worked out. But just hoping that this stuff isn't going to appear on the exam is wishful thinking, all right? That's not going to be the case.
Did you have a question?